So today we're going to introduce the concept of differentiability. Differentiability is a variation on the word derivative, and it is a property of a function. Similar to Chapter 1, the emphasis in Chapter 1 was on continuity. Chapter 2, our emphasis is going to be on differentiability and what that means. So you've learned, I would say we learned kind of our tracing of functions. If we started with Chapter 0, which was our review, we talked about functions being one-to-one, and that being the important thing we needed to come out of Chapter 0. And then in Chapter 1, we talked about functions being continuous. That would be what we came out of Chapter 1. Chapter 2 will be this idea of being differentiable. So I'm going to teach you what the meaning of differentiability is, how to find one-sided derivatives, the same way we did one-sided limits. When something is fails, just like a function would fail or continuity would fail, we'll learn what it means for differentiability to fail and what the implication of having differentiability is. All right, so we're going to start with that. If you remember from Chapter 1, we checked one-sided limits this way. We looked at the limit of f of x as x approached a from one side. We called that a, approaching from the left, and we compared it to the limit as x approached a from the right, and I was really a stickler about you putting f of x after. Or you could put the function that you're working with in parentheses after, but something has to come after the limit. And the reason I kept hounding you about that is because now that we're going to do derivatives, the format approaching from the left and the right is similar, but now you need to have f prime. And so we'll be looking at the derivative on both sides. And remember, every time I use the word derivative, I could replace that with the word slope. So we'll be looking at the slope on both sides of a value, not just the value itself, but the slope on both sides. And so that's why it's going to be important for you to put this here, because otherwise I won't know what limit you're talking about. Are you talking about the limit of the regular function, or are you talking about the limit of the derivative function? You need to have something after your limit, and then pretty soon we're going to talk about the limit of the second derivative, and what does that mean? And all of these things have meanings. When we check one-sided derivatives, this is where the word differentiable comes in. A function is considered differentiable on an open interval if, and here's the requirement, it's continuous on the closed interval. What did we learn before that required continuity as, like it had to be continuous first? IVT. Pretty much everything we learn requires continuity at the beginning. And so the same thing is true here. If you don't have continuity, you for sure don't have differentiability. It's not possible. You have to have continuity first. The continuity is on the closed interval, so note that. That continuity is with closed values on the end, but differentiability is on open intervals. It does not include the endpoints. Continuity does, differentiability does not. And then if you establish that you do have continuity, then you're going to check the right hand and the left hand derivatives. Okay, so you'll be approaching from the left and approaching from the right. If those two are equal, then you have differentiability. So there's three things. One, is it continuous? You have to check that first. 2, check the right-hand derivative. 3, check the left-hand derivative. If it meets all three of those things, then we say the function is called differentiable, or it has differentiability. You can say it that way. Okay, the function is differentiable, or the function has differentiability. Those are just two of the same ways to say the same thing. Okay, so here you go. Here's the process. Step 1. Checking all of these things for continuity. You need to check the left-hand limit. You need to check the right-hand limit. You need to check that there's a closed point. Okay, all of that is checking continuity first. So you have to establish continuity, being all the requirements of continuity are left. If you've checked continuity, and then you realize when you check your derivative that the derivatives are not equal on either sides, we call that non-differentiability. Just like we have not continuous or non-continuity, we have non-differentiability as well. So even though you might have continuity, it doesn't guarantee differentiability. You have to check. If you have continuity first, you might have differentiability. If you don't have continuity in the first place, you will never have differentiability. Continuity is the most important part. Any questions so far? It helps to see what it looks like, what I'm talking about. All right, here's a picture. Show that the function is not differentiable. So the first thing you want to do is establish what the derivative is. Because the function is in two pieces, the derivative will also be in two pieces. The derivative, the first piece would be 3x squared. The second piece of the derivative would be the number 4. And the derivative is on open intervals. All right, I mentioned that earlier. The derivative does not include equal to. Derivative is always open intervals. So you have the original function. Now you have the derivative. Now we're going to go through and show meaning you got to satisfy all the requirements for the math that this function is not differentiable. So step 1, we're going to check continuity. So we're going to check the limit as x approaches 0 from the left of f of x. And so using the function, we realize that that value is 0 when I approach from the left. We will check the limit as x approaches 0 from the right of f of x. That is also 0. And finally, we will check what the closed value of 0 is, and that is also 0. So by checking all three things, we've established continuity. And then the second part would be to check differentiability. And we'll do that by checking the limit as x approaches 0 from the left of f prime. When I check it from the left of f prime, I'm using 3x squared, so that would be 3 times 0 squared, which would be 0. And when I check it from the right of f prime, that's the value of 4. Those two things are clearly not equal to each other, so we say that this function is not differentiable. Although it was continuous, it does not meet the requirements to be differentiable at the value of 0. Visually, you could have told that right at the beginning because we have a parabola connected to a line. And a parabola connected to a line makes that sort of jerky transition from one to the other. And so that also is an indicator that it's not differentiable. But you're not allowed to use, I just looked at it and that's what it was. That's not a, if it's a multiple choice, for sure. But if this shows up on some kind of free response and you're asked to show that it's not differentiable, you're going to have to go through those processes. Okay, most of the functions that we're going to find in calculus are differentiable. Functions that are not broken. Thank you. Did it go down?
No. There's a beep.
Somebody's phone is going off too. Most of the functions we find are differentiable. Okay, they're unbroken, they're smooth, They have nice transitions. Most of them are. But when they're not, they're easy to spot. All right, here are some things that are easy to look for. Okay? Any kind of function with a corner is going to not be differentiable. If the transition from one piece of a function to another piece of a function is not a smooth transition, then it's not differentiable, okay? Give me an example of a function, like the most basic function that has a corner in it. Noah? Absolute value, yeah, a v function. It's continuous, but it's got a big hard corner on it right at the origin. Okay, all right. Another one is something called a cusp. All right, a cusp is when you have two functions that are connected like this, but where the two sides are heading up, or it could be the other way around. It could be like that, okay? If you think about it from a slope perspective, okay, so watch my hands. What's the slope when I'm doing this? Positive infinity. And on the other side, what's the slope? Infinity. Positive infinity. What's the problem with that? No two infinities are equal to each other. And so that's why if the slopes are, even though they're continuous, the slopes are not equal to each other, or the other way, going to negative infinity. So that is called a cusp. Okay. The third one is called a vertical tangent, which is different than a horizontal tangent. It's a vertical tangent. So a vertical tangent looks like this. Okay, and the problem is always right about here. Because if I do the same thing, if I say what's the slope coming at it from the left, and the slope coming out, if it's going vertical, then its slope is infinity. And on the other side, the slope here is also infinity. And the problem is those two infinities are not the same infinity. So again, the slopes are not equal. All right, and then the last one is any discontinuity. So any removable discontinuity, any jump or gap, any infinite discontinuity, any discontinuity is automatically not differentiable. All right, so when we look at this absolute value graph, clearly it is not differentiable because it has a corner. But like I said, unless you're on a multiple choice or like a matching section or something, you got to come up with a reason why it's not differentiable. Okay, right, but that there's a corner doesn't work. Your reason has to involve limits. Okay, so although we can clearly see we've got a corner. So let's think about why that might be. What is the derivative on the left? And when I say derivative, remember what word can I replace that with? Okay, so what is the slope on the left of an absolute value function? -1, perfectly. And what is the slope on the right of an absolute value function? +1. Those two things are not equal. Okay, and so you have to use the words of slope, the words of limit to be able to explain it. So on the next page, here we go, here's our proof. The equation for an absolute value function is piecewise. That's the equation for what would make an absolute value. So if you want to jot that to yourself, this is the shape of an absolute value. It's -x on one side, which is a negative line with slope -1, and then +x on the other side. So the left-hand limit, so limit as x approaches 0 from the left of f of x is 0 because it's approaching the origin, and the limit on the right of f of x is also 0 because it's approaching the origin, and f of 0 is 0 because it meets at the origin. So that establishes continuity, but even though the absolute value is continuous, we can show that it's not differentiable by showing the derivative. So the limit of the left of f prime, you guys told me was -1 because the slope was -1. And the right-hand derivative of f prime is +1. And because of that value, that's the proof. Using one-sided derivatives, the derivative on each side, that's the proof that this is not differentiable. That's how that would look. Okay, here's an example of a cusp. The cusp is clearly continuous because the left limit approaches the origin, the right limit of the function approaches the origin. They meet at the origin. It's clearly continuous. And so that, but we would say it's not differentiable because, again, when we check f prime, the slope approaching the origin, on the left side, the slope is -infinity. It is appearing to go down vertically. It's getting, if I zoom far enough in, it's steep enough that that is a negative slope. And on the other side, approaching from the right, that appears, even, you don't even have to say it's -infinity. You could just say it's negative. The slope on the left is negative and the slope on the right is positive. And those are two different numbers. And so that's not possible for that to be differentiable. Here's a graph of the vertical tangent, same idea. Okay, same idea, that the limit on both sides of the slope values, although continuous, the slope values are not the same. So we have the limit approaching 0 from the right of f prime, let's do 0 from the left first. 0 from the left of f prime is +infinity. The limit approaching 0 from the right is also +infinity. However, those two infinities are not equal to each other. All right, almost done. Okay, a good way to just sort of think about differentiable functions is what we say they are locally linear. Locally linear means in any given section on a graph, if you zoom in, it will eventually look like a line if you zoom in close enough. No matter how curvy the graph is, if you zoom in close enough, in that locality, it will be linear, that it will eventually look like a line. So let's see, in the jargon of graphing calculation will look like a line. When we zoom in on them. Okay, so I did some screenshots. I have a graphing program. So here's the graph on a window of -4 to 4 and -3 to 3. And so you can see it's very wavy. But if I pick any particular point, and I decided to pick the point right here. If I pick that point and I zoom in, okay, now the graph looks like this, and I was still focusing on the point right here. And then I zoomed in on that further, and now I'm, okay, and it's starting to straighten out. It's starting to lose its curve because I'm looking at a small locality. I'm looking at a very focused, hyper-focused in little spot. So if you can do that at all points on the graph, then that is another way that you can establish that it is differentiable. It doesn't work on an absolute value. Because no matter what, if I zoom in on that point, that origin on the absolute value, that corner is never going to go away. That corner will always be there. The closer I get, it's still going to be a V. No matter how far down I go, there's still a V here. Okay, and if I just keep zooming in, it's still a V no matter how far I go. And so that is not differentiable because it's not locally linear. I can't make it look like a line. All right, so here's our our takeaway from the day. If f is differentiable, didn't spell right. Differentiable. Okay, If I tell you this function is differentiable, what can you assume must also be true? It's also continuous. If I tell you it's differentiable, that means the implication it implies it had to have been continuous. I can't tell you something is differentiable for a discontinuous function. The reverse is not true. If all I tell you is that something is continuous, am I guaranteed it's differentiable? No. It might be differentiable, but it also might not be differentiable. Okay, differentiability guarantees continuity, but continuity does not guarantee differentiability. And if anybody asks you to give an example of that, just give them the absolute value as an example. Absolute value. It's continuous, but it's not differentiable.